In this video, we'll be covering the concept of an alternating series. Now, it's important in terms of an alternating series to understand that it, well, alternates. Most of the examples that we've done in the past, they require that the series terms be all positive or in some way increasing. So this is one of the few examples where it says, hey, guess what? We're going to take all of those terms that we decided had to be positive, and now we're going to talk about how do we deal with the ones that have alternating terms where they're positive, negative, positive, negative, positive, negative. So the first series that we're going to look at in this case is something that looks like this. The summation of k equals 1 to infinity of negative 1 to the power of k plus 1, all divided by k. In this case, this series is actually going to appear as an alternating series because it's negative 1 to the power of k. It's going to bounce back and forth to positives and negatives. So if I plug in 1 to this, I'm going to have a positive number on top because negative 1 squared is positive 1, and I'm going to have k as 1 in the denominator. So 1 over 1. My next one is going to then be, when I plug in 2, I'm going to end up with a minus 1 over 2 because the top is now going to be negative. So technically it's a plus a negative. And I'm going to go ahead and write it that way to keep things relatively consistent. The next one I'm going to go ahead and add, and when I plug in 3, my top value is now going to be positive again, and I'm going to have 3 in the denominator, and then plus again a negative 1/4, and so on and so forth. This is going to simply alternate back and forth where I'm positive, negative, positive, negative, positive, negative, and so on, whatever. Every series that has some form of negative 1 to the power of k or negative 1 to the power of k plus 1 in some form is going to be some example of an alternating series. Now, this rule might change depending on how the exponent appears, but if it's k or k plus just a number, we can almost guarantee that it is some form of an alternating series. Now, that doesn't mean that the alternating series is guaranteed to do what we need it to do. There are some very specific steps to determine whether or not that particular series, which is alternating, will converge. So let's go ahead and look at this series to begin with. If we were to use the basic rules of determining whether or not a series is convergent, and I'm not using the methods or the types, I'm using the basic rule. And that basic rule is talking about the limit of the partial sums. So we're going to go ahead and look at the limit as n goes to infinity of s sub n, and we're going to have to figure out what n does. Well, the first sum is simply the sum of the first term, so that's just going to be 1. And then the sum of the first two terms, that's 1 and negative 1/2, that's going to be a positive 1/2. And then when I do s sub 3, I get something like 5/6. And when I do s sub 4, I get 7/12. Now, if you look at these carefully, it starts out at 1, it cuts that in half, it goes a little bit above 1/2, and then it bounces even closer. So if you were to compare all these in terms of twelfths, this is 10/12, this is 6/12, this is 12 over 12. And you'll notice that these terms are definitely bouncing 12 to 6, 6 up to 10, 10 down to 7. They seem like they're bouncing back and forth. So S sub n appears to converge. Now, we could attempt to prove this, again, using specific methods from previous videos, but what we're going to do is we're just going to go ahead and say, well, let's talk about what it means for an alternating series to be convergent. This is what we call the alternating series test. And again, I'm always lazy, I always abbreviate that, alternating. So ALT will stand for alternating series test. This will test whether or not the series is actually alternating and, more importantly, will actually converge. There are two specific details that have to occur. So if I've got a series that has a negative 1 to the power of some form of k or k plus 1 multiplied by some other portion of the series, so a sub k. So again, up here, you would have negative 1 to the power of k plus 1. Down here, the a sub k would simply be just 1 over k, because this negative portion to the power of a k is somewhere else entirely. I can shift it aside and put it next to the series that we're actually talking about in terms of the non-alternating portion. Now, the two details that we have to conclude or check before we can conclude convergency is, number one, the terms in the series are non-increasing in magnitude. What this really means is that my a sub k values have to be either decreasing or constant. This allows things so that these things aren't bouncing far and above the things we're looking for. So again, technically we can have an alternating series where these things aren't decreasing in value. So it goes 12 and then it goes up to 13 and then it goes down to 10 and then it goes up to say 14, and these are obviously not decreasing in value. They are increasing in value based on magnitudes. So again, we're talking about the terms of a sub k. Now again, the way that we would prove that is simply by looking at a sub k as some kind of f of x function. And we do this in the integral test. You simply take the derivative of that function and ask yourself, is the derivative negative? Because again, if we want non-increasing, then we just have to make sure that the terms are decreasing, and decreasing for calculus is simply the derivative has to be negative. The second detail we have to prove in an alternating series to conclude convergency is that the limit as k goes to infinity of a sub k has to be equal to 0. Now, recall that this statement right here focuses in the understanding of the divergence test. If we end up getting this for the divergence test, then we end up inconclusive information for a basic series that has positive terms. However, with the alternating terms, we can conclude then that number one, the terms of magnitude are non-increasing, meaning they're getting smaller and smaller, and not only are they getting smaller and smaller, but the terms themselves are then eventually getting to 0. And the fact that them getting eventually equal to 0 means that we're slowly adding back and forth numbers, positive and negative, canceling values out until we're just adding zeros the entire time. So this logically helps build and helps logically make sense out of the overall understanding of what the alternating series does and how it works. Now again, there is a proof to this. It does have to deal with this monotone increasing concept, and it has to utilize the understanding of the limit of partial sums. We won't do that in this video. We're just going to go ahead and focus on these are the rules we have to apply to utilize and conclude an alternating series, a series with -1 to the power of k or k plus 1, will converge.